Okay, so we're getting into something interesting here. Now we're going to talk about energy. And energy is important to a chemist or a physicist because, first of all, it's defined as the ability to do work. But a chemist is more interested in it because it helps us determine if a reaction has happened and what reaction has happened. Okay, so more broadly, it's defined as something that energy is some energy makes objects move. Okay, it's the ability to do work. Now our objective here for this section our learning goal is to identify energy as potential or kinetic, so we'll define what those are, and we're going to convert between units of energy. Okay, so first of all, kinetic energy is the energy of motion. Examples of the following of kinetic energy examples are the following: swimming, water flowing over a dam, working out, a ball rolling down the road, okay? A car moving down the road, that is kinetic energy. Potential energy is the energy that's stored for use at a later time, and we oftentimes say the energy of position. It's determined by the position of an object or a chemical composition of a substance, okay? So examples of the following: water at the top of the dam has kinetic energy, a compressed spring has kinetic energy, and chemical bonds in gasoline, coal, or food. Those are potential energies, okay? So let's do a learning check real quickly. Pause the video and make a guess. Are these potential or kinetic? Okay, so I'm going to assume that you pause the video and come back here now. Rollerblading is definitely kinetic energy, right? Because you're moving down the road. A peanut butter and jelly sandwich is probably not doing anything, but just sitting there. That is potential energy. Mowing the lawn is definitely kinetic energy because you're moving around. And then gasoline sitting in a gas tank has potential energy. All right, so now let's talk about heat and energy. Heat is the energy that's associated with the movement of particles. Okay, so the faster the particles move, the greater the heat or the thermal energy of the substance. So if you have an ice cube, as you add heat to it, the water molecules move faster. They increase their motion, okay? And they eventually have enough energy to change the ice cube from a solid to a liquid because they're moving so fast, okay? So heat is the energy, again, heat is the energy associated with the movement of particles. The faster they move, the more heat that you have. Okay, so units of energy that we're going to be interested here, in which we're going to be interested, is joules and calories. And so our core chemistry skill is using units of energy. Okay, so the SI unit is joules. You probably haven't heard about that a whole lot. We oftentimes say kilojoules. Calories, you probably have heard about that because that's really common to talk about calories in terms of food, right? So a kilocalorie is usually what we mean by a calorie. When we say a calorie, we usually say a capital C. How many calories does that piece of turkey have? And we're really talking about kilocalories. Lowercase c, well, I'm not going to use that term in this course, right, because it's confusing. I'll use kilocalories, and I'll use lowercase c calories, all right? And a kilocalorie, of course, is 1,000 calories. So the calorie is defined as, this is a definition, the calorie is defined as the amount of energy needed to raise the temperature of 1 gram of water by 1 degree centigrade. Interesting. A calorie is the amount of energy needed to raise the temperature of water 1 degree centigrade. 1 gram of water, 1 degree centigrade, okay? And this is also a definition. It's exact. All right, so 4.184 joules is 1 calorie. Okay, so let's do a little comparison here. The energy that's radiated by the sun, energy radiated by the sun is about 10 to the 26 in 1 second, is about 10 to the 26 joules. That's a lot, right? You can imagine by far most of that doesn't even get to the Earth, and we still have a lot of solar energy when it gets here. Amazing, really. The world reserves of fossil fuel, unbelievable. Look at that. We have a lot of energy reserved in fossil fuels. Amazing. Okay, energy consumption for 1 year in the United States, okay, is 10 to the 20. Okay, solar energy reaching the Earth in 1 second, 10 to the 17. That's a lot, right? As I said before, okay? Now, the energy use per person in 1 year in the United States is 10 to the 11 joules. Still sounds like a lot, right? But that's just one person, right? And then energy from 1 gallon of gas. Are you serious? 10 to the 8 still sounds like a lot, right? But look at 10 to the 26 looks like this. 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. That's what this is, right? And 10 to the 8th is what sounds like a big number. It's way smaller. It's like billions of billions times smaller, right? Energy from 1 serving of pasta, a donut, or needed to bicycle for 1 hour. 10 to the 6. Oh, wow. That's a lot of calories, and that's a lot of joules in a donut, isn't it? And then we actually use energy to sleep for 1 hour. Really? Wow. 10 to the 5. Okay, so that's sort of interesting. Let's wrap this up with an energy with a learning check. And I want you to pause the video and then come back and check your answer against mine. Okay, so the question is how many calories, right? And so I'm going to do the picket fence method because I like it. And I'm even going to do a straight line because I like it. Okay, and so I'm going to do calories because calories are here. And I'm going to go calories per joule, right? And so joules got to cross off. I got to put that there. Okay, this is not so bad. Look, it's 150. Whoops, 150 joules. And we know that there's 4.184 joules for every 1 calorie. So this looks like this is 2 sig figs. This is 4 sig figs. So our answer is going to be 2 sig figs, okay? And so let's say 150 divided by 4.184. And that's going to give us, whoop, got it wrong there. Just a minute here. 150 divided by 4.184, which is 35.85. 35.85 dot dot dot. And this has to be rounded. So that's going to go up because it's an 8. It's going to be reported as 36. All right, so that's an introduction to energy. We'll be seeing more of this later.